Hello everyone, welcome to the Electronic System Design Laboratory course in autumn semester 2020. A brief background of this course is that, as you know, this is a 2-credit lab course having 3 contact hours per week, and this is probably the only lab in your academic career in this institute which shall not be supporting any theory course but rather will be a mix and match from here and there, if you will. So this lab will in particular attempt to give you a feel of analog electronic design. So it is not just any electronics we are going to do. This is going to be analog electronics. So this course will not only comprise of certain experiments but will also be driven by different projects. So therefore a part of this project is an opportunity for you to create something on your own, a masterpiece out of your ideas, if you will. So majorly, if as far as the grading is concerned, 30% will be for lab work. That includes all your attendance, lab reports and individual efforts. 10% for how well you pitch your project idea. So I shall discuss about that shortly. 20% weightage for how well you demonstrate your project or mini project, and 40% weightage is for the semester end viva voce or the examination for this lab. Now, part 1 until the mid semester will involve analysis and design based experiments. Either the circuit will be given to you and you will have to come up with some parameters or do some particular measurements or design the circuit values for certain applications, or you will be given specifications and you have to come up with a circuit to meet those specifications. So few of these experiments may stretch up to 2 lab sessions, and in parallel we shall also have a series of video lectures where we shall look at several theoretical and practical aspects of system design, including this particular video. Now, this looking at the fact that we are all away from our homes, we are away from the department and the institute, we are all at our homes. So therefore, these experiments will be simulation based and there will be no concept of group work for the experiment part of the course. So all of these experiments have to be done individually, and we shall be using ngSpice, which is a free simulation tool. However, we shall not tie you down. You are free to use other free softwares also, for example LTSpice and TINA from Texas Instruments. But the circuit and system data which you may need, for example the device libraries and sub-circuits, we shall give you for ngSpice. If you can make them work with other softwares, well and good. But so ngSpice is the major software that we shall target. So we shall not be tolerant to any amount of unfair practices, including copying of reports or duplicating experiment results. And in this course, if you are not getting a result, it's better to say that I am not getting a result, but I have done so and so things and deserve credit for your honesty, rather than copying your friend's results, which will not only perhaps give you a 0 if you're caught, but what is more important is that you are not going to learn that way. So if you are caught copying or using unfair means, you will straight away be awarded a 0 for that particular experiment, irrespective of whether you have copied or you are the one who has generously given their data for copying. Now comes part 2. Part 2, some part of the post mid semester time will include maybe 1 or 2 experiments. Now, during this time, you shall be divided into groups of 2 or maybe 3 for the design project. Now, I shall announce those groupings well in advance. So you will spend considerable time discussing project ideas with your group members, and then you will pitch them to the instructor, that is me, for approval. So so this is what I meant by that 10% of your grading weightage. So how well you pitch your idea, that this will decide that grade. So once your idea is approved, you may start your analysis, design, simulation work, and whatnot. The idea is that you have to make your design on a printed circuit board. You will get a feel of designing a system with permanent connections. So this we are expecting, if at all you return to campus during this semester, we shall do it at that time. If not, then perhaps we will not be able to do this. But let's be hopeful. Now let's discuss a little bit more about this so-called project or mini project. So as I discussed, you will be working in groups of 2 or 3, and the grouping shall be decided by the instructor, that's me. Now after your grouping is done, you will discuss, you will come up with an idea which you will present to not just me but to the whole class. And it cannot be a textbook idea which you can just pick up the circuit from a book or a magazine or some internet source and just check it out. No, that's not what we're looking for. We are looking for something very interesting, perhaps something application oriented, something which you don't come across so easily, but at the same time it could be a very exciting solution for some existing problem. I'm not saying that we need to do research, but it would be a good idea if you can rack your brains and come up with a good idea. Now, good ideas means that you should be able to do this project in 3 to 4 lab sessions at the most. No further time will be given for this. So that means 3 to 4 weeks roughly. Now, this project will be an analog design project. You are allowed to use op-amps, you are allowed to use analog switches, you can use transistors, diodes, whatnot. I shall also allow you to use basic gates, that's digital chips, which you may have used in your DEC lab. You are allowed to use them as long as they do not contribute to more than 20% of the system functioning. Any more and they shall be not permitted. And other miscellaneous components, for example, if you want to use some kind of a sensor or LEDs, switches, you're allowed to use those. There is a total blanket ban on using microprocessors, microcontrollers, FPGAs, or any other programmable platform. That is not allowed to be used. Last but not the least, looking at the current COVID situation, you will have to look at the time of the demonstration of this project. So select an idea which can be demonstrated even remotely through simulation. All right. So even if you are not able to fabricate your design on the PCB, you can show your idea working by means of a meaningful simulation. So that is something which you could think of. Although this is not a very binding constraint on your project. I mean, we are willing to make certain relaxations depending on how good your project idea is. So it's easy to be confused and scared looking at this both experimental as well as project approach to this course. So as I mentioned, we shall be having a series of video lectures also to give you a feel of different aspects of design. And so also for this we have made a rough planned progress during the semester, when our first lab session will be on 21st of August. While we do the experiments, we shall also give you a few video lectures, and the session on the 11th of September shall be completely devoted to having a hands-on session, a live session, if you will, on PCB design and computer-aided design tools, where you will learn the different basics of PCB design and whatnot. So essentially the 4 videos will be today's. That's the introductory video and the different aspects of electronic design. Then comes how do you read data sheets, interpretation from data sheets and the help in selection of components for any project. Then the video, as I mentioned, on PCB design. And last but not the least will be a video on how to test, debug and troubleshoot your circuits. That's very, very important. So, and as you can see, after the mid-semester, we will have the project idea pitch and approval. And almost the entire of November, you will get time to work on your project. And finally, on 4th and 5th December, we will have the project demos and the lab evaluations. So let's start with the question, what is electronic system design? So after having spent over 3 years in electronics, you know the meaning of the word electronics. Now, how do you define system? So system is nothing but the interconnection of known blocks. Now, what do you mean by blocks? The meaning is different. It can be a small diode, it can be a small resistance, it can be something big also, like a processor, it can be something big like an op-amp, anything. And the word design means, given certain specifications, the process of converting those specifications, which we lovingly call as specs, into a system comprising of known elements. For example, if I tell you, design an amplifier with a gain of 100, what can you use? You can use an op-amp and 2 resistors, where the op-amp and resistors are examples of those known elements. So the definition of known elements differ from person to person and scenario to scenario. So there is no single meaning of known elements. Known elements are something whose performance you already know. They can be simple, they can be complex. Now let us take an example of, or rather before that, let us take a look at the general flowchart of electronic system design. So as I said, we start from specifications, and from the specifications we try to identify the underlying blocks. So there may be those blocks comprising of known elements, and once all of those blocks are identified, we essentially start doing the work, and those work essentially has 3 particular or 3 broad functions or tasks. That is, one is simulation and circuit verification, and using that to build the circuit for each block, and in parallel building the necessary software. Now notice that I am talking about a general system where you may use microcontrollers and FPGAs also. So therefore this part of the discussion is rising above the course where we are binding ourselves only with analog. So therefore there is no need to write a code as such, but in general you should be aware of the whole process. Had we been on campus, I would have preferred to do a whole electronic system design as far as possible. Now, once all these 3 tasks are completed, you integrate and test them on the breadboard wherever possible. If it's not working, you go back and check for errors in one or more of the previous steps. Now, once your initial results or testing is complete on the breadboard, you go to the next step to make it into a permanent solution. That is what is called as a printed circuit board. So you may have noticed that most of the commercial deployment of electronic systems happen in the form of PCBs. Nobody uses breadboards to deploy circuits commercially because they can get loose and all sorts of things may happen. So therefore we print our circuits on the board where the connections are permanent. So, and this is a very important step, because once you fabricate a PCB, there is probably no going back. So once your PCB is ready, it comes back. After fabrication, you assemble all the components, solder them, and then you go for the final testing and troubleshooting. So in case there is a major fault in the final test, which is not a good sign, you need to go back and refabricate the PCB, which generally costs a lot more money, and it is not a good sign. So therefore most of your troubleshooting should happen before the PCB is ready. With this, let us take an example of a system which is not analog, but it consists of analog and digital parts both. Now, I am not giving this example, I'm giving this example to you to show a general example of electronic design. Irrespective of the fact that we shall be largely focused on using our knowledge to build analog systems. So let's see what the problem is all about. So the problem is given as you are asked to design a system that measures and displays the strength of the 4G mobile data signals around it. So essentially it is a monitor system which shows what is the strength of the mobile data signal that is around the system. So the specifications are the following. It should be obviously able to capture 4G mobile data frequencies, and after capturing it should be able to display the signal strength on a small LCD screen. Okay, it doesn't say small, but I'm saying that. It should glow an LED in case the signal strength falls very low, below a certain threshold. The system should repeat measurements and refresh the display periodically to show as the fluctuating signal strength as and when they do. And the whole system should be powered using a 9-volt battery. With these 5 odd specifications, let us now see how to translate these sentences into circuits. So what's the first spec? The first spec is to be able to capture 4G mobile data frequencies. So how do you capture signals? How do you capture wireless signals? You need an antenna. So you need an antenna which works in the frequency range of 2.3 to 2.4 gigahertz, which in India is the allotted frequency spectrum for the 4G signals. Now, once I have captured the signal, what do I need to do? I need to measure its strength. So for that, we need a hardware piece called as the power detector or envelope detector. This you may have come across in your communications course. So a power detector is a circuit which measures the power of the input signal and gives a voltage output that is proportional to the power level. Now, once you have this voltage corresponding to the power level, you need to digitize it because you cannot display analog values. The value that you get from the power detector is an analog value which you cannot display directly on a digital device like the LCD. So therefore, you need an A to D converter, and thankfully most microcontrollers these days have built-in ADCs. Now, now to display the power levels, you need to use an LCD screen. So what LCD should I use? There are so many LCDs available in the market. So thankfully, since we want to see only the power, a small 8-bit LCD with 16 characters at the most should be quite sufficient. Now, as you know, if the signal strength falls, as we discussed, the system must glow an LED to indicate the same. So the LED is very easily available, and the microcontroller has to refresh the display periodically by doing a repeated measurement, so that you can decide, let us say after every 100 milliseconds. That has to be written in your program. Now, if you recall the last point, that was the point about using a 9-volt battery to power the whole system. Now, this is very reasonable because most systems which we would like are standalone handheld systems which should be battery powered. Let's say a 9-volt battery is a very commonly available battery. Now, in spite of the fact that you need you are given 9 volts, but most parts of your circuit may work with 5 volts, for example. So therefore, you will need a linear DC regulator to step down and provide a constant voltage supply for the rest of your circuit, to step down 9 volts into 5 volts and feed the rest of your circuit. So this is how my proposed system block diagram would look like once I have identified all of the possible hardware elements. So the first, as I said, the antenna, it will feed the power detector, and the output of the detector will go to the A to D converter, and then the microcontroller will execute as per the program that you've written and to display the power reading on the LCD. And this process of measurement and refreshing this display periodically is controlled using a timer, and the LED is there with a port in case the signal strength goes too low. So how low you can define the threshold. So let's come to each of these parts. Antenna. What do we use? Do we use commercially available antennas available in Amazon, or do we use a printed antenna which we can design ourselves? Now there is no particular answer. One of the most important reasons for this course is that you will see that more than solving the problem, it is to deal with the choices available in front of us, which is much more challenging. So, both commercial antennas and printed antennas, they have their own pros and cons. So the question now is that the factors you have to consider. You want your signal reception to be specific in a particular direction, or do you want something? Do you want an antenna which can be able to receive signals from all sides? So if the second, then printed antennas are perhaps better. Yeah, and the gain or directivity of the antenna, how strongly it can receive signals from a particular direction. In that case, commercially available antenna might be better. Now the antenna profile. Do you want the antenna to stand out from the rest of the circuit, or do you want an antenna that can be easily integrated with the rest of the circuit? So again, different applications want different things. So you need to play to your strengths. What you can design versus what will be useful for the circuit as a whole. Yeah, now comes the RF power detector. So what are the factors for this particular block? It should be able to detect weak signals, also called as MDS, or the minimum detectable signal. So all power detectors are able to measure the signal power level and give the proportional voltage output. There should be impedance matching. It's a very important factor. You're working with very high frequencies. So impedance matching is something which is extremely important. Whether the impedance of the power detector matches the impedance of the antenna for maximum power transfer and zero reflections. Then input output linearity and dynamic range, how linear is the device, how low of or how weak a signal can it measure, and most importantly, or very importantly, packages for soldering. Now these are available in very small packages. So is it easy to solder it on the board or not? So these terms are there in data sheets of the device. Not all terms will be known to you. So therefore, understanding the product would be very difficult. As an example, I have chosen 3 power detectors which are available in the market with different specifications. Now, which one will you choose? You can see the package for the first 2, that is 4003 and 2015, are SOIC, and 5513 is the QFN package. So it shows that QFN stands for quad flat with no LEDs, and it's a much more difficult to solder package. But does it mean that ADL 5513 is bad? No. You see, its minimum detectable signal is minus 70 dBm, which is a very low signal it can detect. So it's better than, let's say, 4003. As far as matching is concerned, only 2015 is internally matched, whereas 5513 is very highly linear, whereas 4003 and 2015 has limited linearity. If you look at the cost, the costliest is $10 and the cheapest is $1. So it's all about trade-offs. There is no clear winner. Now you need to see which of these 3 ICs you will pick. So you will only be able to make a choice once you read the datasheet and understand what it is trying to tell you, and in what way would those parameters be useful for your design. Now, going to microcontrollers. Now, this is something I should not have to spend much time on. There are multiple choices available to you, but the most important thing is whether you should go for a standalone microcontroller or a whole platform, for example, the Arduino. Most designs tend to use a whole platform, but if you really want to make a low cost and a very small compact system, you should go for a standalone microcontroller. Quickly, I'll just talk about a point about the program. Should you use C language or assembly language? I mean, most of you will say C, obviously, because it's versatile, it's something you know. It's much better than remembering all those tiresome instructions for any microprocessor or microcontroller. But there's one point which I would definitely like to share with you based on my own experience. That is, if you really want to optimize and fine-tune your microcontroller or stretch its performance, then assembly language is the way to go. For example, a few years back, when I was a student, I was trying to make a microcontroller generate a frequency of 50 kilohertz, but I was unable to do so using C because the time taken to execute one C program line was comparable to the time period for the 50 kilohertz signal. So therefore, it was not able to do so. But I did this using assembly, and lo and behold, I was able to generate not just 50 kilohertz, but up to 65 kilohertz also. So therefore, I was able to stretch the performance of the microcontroller using assembly. But ultimately, you are the designer. Whatever works best for you, that you should choose. So the LCDs are fairly straightforward. They are commercially available. You can just go for different options. LEDs are interfaced in two major configurations, sourcing or sinking. So that depends on how much current your microcontroller can absorb or how much current your microcontroller port can supply. And regulators are also fairly easily available. You will see that 7805 is a 5-volt regulator, and I have used a certain number of capacitors at the input and output of the regulator. I leave it as an interesting exercise for you to think and find out why I have used capacitors. So once you are ready with your circuit, all simulations and all parts identified, you will start making the schematic. Now, this is not the schematic of our radiation circuit or the 4G signal strength measuring circuit, but it's a different circuit. But this is what a good schematic looks like. Different parts, different ICs are all connected together, and labels on each side, on each part of the circuit. So once you have made your schematic, you will design a PCB layout. The layout looks like the first figure on the left, that is the black and blue combination. The software which we are going to use for making PCBs designs is called Eagle, and it allows you to do a lot of this artwork on the board. And once your design is fabricated, I have shown you what this PCB looks like from top and bottom. It is not once again, it is not the PCB for this 4G spectrum power measurement, but for a different circuit. But you can see that the top side and bottom side both have connections, and while we will mount most of our components and solder them on the top, there are a multiple number of connections on the bottom side also. So once you solder the components, this is what the board looks like. If you notice the second picture on this 19th slide, is only the connections and the printed legends. Now we have, once you solder and populate the PCBs, this is what it looks like with all the components. So we shall look at each of these aspects in more detail in the next few weeks. With this, I would like to conclude this particular talk, and I hope that you will have an enjoyable lab in spite of being at home.